So this should work now. Still see it. Oops. What's this? So these are now these data points that I just sampled randomly. We will use data points that are more meaningful in a second, but I just need some data to start writing the discrete Fourier transform implementation. So this is just some how do you call it, mock data or whatever. So the important thing now is that we want to implement, oh, there's my other stuff, that we want to implement the formula for the, oh, we can also do it differently. We can also look into the script, and I don't have to write this. So we take it straight from the script. So this is what I just wrote by hand. This is also, of course, in the script. And this is what we have here. So, and we want to implement this, and we now have some data. So the data was called y in MATLAB. It's called yk with this little thing in here, but it's n data points. And we want to pass this now to a function that evaluates this definition of the discrete Fourier transform. So let me find MATLAB again. So we write another function. This is just for the moment here. We write another function which returns this nth order sequence big Y, and we pass to it our original data. And this function evaluates the discrete Fourier transform of the input nth order sequence Y using the definition of the discrete Fourier transform. Because which is different from what the fast Fourier transform algorithm does. So what I'm also showing here is that you can also compute discrete Fourier transforms without relying on the fast Fourier transform algorithm. And it's also quite fast. So the inputs to this function are y, which is 1 times n vector, or yeah, if you don't know what a vector is, then we rather write an nth order sequence. And the output is obviously big Y, which is an nth order sequence of data values, let's say, of DFT values. Oh, that's helpful. Where we can, then we have it directly here. We don't need to switch screens, where yj is defined, and this is just the definition of what we've seen. Yn times the sum from k equals 0 to, let's do proper LaTeX here, k equals 0 to k equals n minus 1 yk. This was our integral over the function values fx times exponential of minus 2 pi j divided by n times k, and somewhere is an I missing, so let's put an I in there. Yeah, so this is just the formula that we've just seen, which is just the definition of the discrete Fourier transform values, and computes this let's do it like this, for j equals 0, 1, and minus 1. So that's just the documentation for our function that we just now want to write. And then the first thing that we of course need to compute this is the number of data points. So we can evaluate this as follows: sequence length n is length y. So length is just a command in MATLAB that gives you back the number of elements in y. And to debug the whole thing, let's already call it. So what I'm doing now is I'm passing this data sequence that we just sampled here and then visualized a bit crappily there. I'm passing this into this function, and then I can look what I get in this function. So my MATLAB is missing. Too boring. Implementation. Good. And that's debugging. This is when people learn programming, they often end up in my office, but that's when you should go on. So the n here now, because we are currently in the execution here, is 16 as we've specified above. So now we need to if we want to evaluate this function, we need to specify the index vectors appropriately. So we need to set the j and k vectors, and these are running, as you can see here, from 0 to n minus 1. Yeah, k runs from 0 to n minus 1. So we just define two vectors, j, which runs from 0 to n minus 1, and another vector k, which runs from 0 to n minus 1. So just to be clear, so j is now this, running from 0 to 15, and k runs from 0 to 15 as well, as required for these formulas. And initialize our output, the DFT of y, by, this is what I like to do, by nonce. So these are not numbers, so that we have already the array that we are interested in, but they are filled not with numerical values, but with these MATLAB nonce, which just mean that you cannot compute with them. If you add something to them, they are again none, which is good for safety, so that you don't add. So if you initialize things with the zeros or ones, you always have the problem that you don't really see if something goes wrong. Then we now want to compute each of these values y, and we have this formula for it. So we do a nested for loop. So we iteration over values yj, because we need to compute it for j from 0 to n-1, and because we need I as the complex number, and we have a value, a vector called j. We don't use the typical iteration variables I and j now, but we use a and b. Normally I would use for the first for loop I and for the second for loop j, but here they have some meaning, so I'm not using them. So we're going, and this is, in a way, the 0 to n-1 is nice if you're not doing things with MATLAB, because usually iteration indices start at 0. In MATLAB, they start at 1. So, whatever. Now, well, what we need to do is we need to form the sum, right? So we need to form a sum from k 0 to k n-1, and so we need to add things, and of course this adding things can also be done in a for loop. So here I'm then, although I just told you that I'm not initializing things at 0, I'm initializing the sum at 0. Initialize yj to 0, and then I'm forming the sum here. So I'm adding for each k, I'm adding up what this formula says. So iterations over values yk. So here I'm using b now as the running variable, and the yj, which because we have this running variable a, then is given as ya, so as it was before, plus the current contribution. So 1 divided by n times y b, so that's our yk, times the exponential, which was MATLAB, minus 2 times pi times, for some reason I have here 1i. So in principle I is just a complex number. 1i is maybe some safety things, because I is also often overwritten in terms of a running variable. Maybe I use 1i here because I have it in my earlier version. That might make sense. So, but this is just this I here. And then we have our j, that's ja divided by n times kb. Yeah, so this is just translated to MATLAB code, this formula, and note that the summing is done via a for loop. Yeah, so on the first iteration we add the first k0 thing, then on the second we add the thing that is k1, and so on. So iteration over yk for some k equals 0 to n-1. So let's see whether this runs, or if I still have some bugs in there. I have. Where was this unexpected MATLAB expression? Oh, times. So, and now we have evaluated the discrete Fourier transform, and as you see, what we get out of that, not too surprisingly, are complex numbers. Yeah? So our y, you see here how it's written in MATLAB. So you have, this is the real part and this is the complex part. So for example, if we look at our y1, y1, the complex part is 0, but here for y2 we have the real part of y2 is minus 1.241 and the imaginary part of y2 is 0.175. Now we've applied it to some random data, so that's not really helpful if we want to figure out whether this made any sense whatsoever. So what we now doing, and what I actually, so to get an idea about the whole thing, is that we create some data where we know the frequency content. Yeah. So remember we did this very early on when we talked about the real Fourier series, that we added like 3 cosine functions of different frequencies and different amplitudes, and then we looked how they look in the script, and so we are kind of familiar with that. So let's create some meaningful data now with some more data points. Questions right now? So far I've just implemented the formula of the discrete Fourier transform. Not much happened. So now let's see that we can interpret what we get out of the Fourier transform a little bit more. So let's do a data simulation. So let's use number of time points, maybe a little more. Let's specify a sampling frequency. And here I have 2 to the power of 8. Is that 256? What is this? Yeah, so the sampling frequency is now 256, which means that the if we are dealing with temporal data, the step, so let's comment here. So that's the sampling frequency. 256 hertz. Then if you have 256 samples per second, then between any 2 samples, it's of course 1 divided by 156 seconds, so that's the time increment. And seconds, let's see what that is. So that was our, we had 500, right? So I would have gone to 2 milliseconds. And he decided it's maybe not that boring. The MATLAB business. Which also means we can establish a time vector by going from 0 in steps of dt to n-1 times dt. So this is now our time scale. So these are many samples, and they go, so this is kind of EEG style things, so they go in steps of 4 milliseconds, and the time points are 0, 4 milliseconds, 8 milliseconds, and so on. But there are many samples. And now let's set up some data where we know the frequency content. This is the whole point. So that's time domain vector or whatever. And let's define some circular frequencies. Let's say 0.5, 2, and 3. So I want to create data that has cosine frequencies with a circular frequency of cosine components. Of course, one can use more or less, or whatever. I'm not dealing, so I'm not doing any sign contribution, so that we don't need to specify that much. So these are now, if you think about the real Fourier series or just a linear combination of cosine functions, these are now the AK for these cosines of 2 pi times omega t. So the AK is whatever, so let's say 1.5, no, that's, then we have the same, 0.2 and something like this. We will see, we will look at the signal and you would say, and I always say it doesn't really look cool, so let's change something. So these are the cosine amplitudes, the AK, if you want, cellular frequencies, which were the omega k. And now let's create the signal, iteration over frequency components for k to 1 length omega. So we are just adding these 3 cosine components up. Our y, which we might as well initialize to 0. Someone might point about initializing things at nonce doesn't really hold true today. So we first create some data that is 0 for all time points, and then we add to it cosine functions of varying frequencies and amplitude. So we do y plus a k times cos 2 pi times omega k times t. So this relates back to our first work on generalized cosine and sine functions. There we would have, so if you think about the whole thing, then there would be this other term here. But so this would be the full thing, but I'm setting all the bk to 0 so that we have a little bit more control. I mean, everything is then in phase in terms of cosine. And let's have a look at the data then. No, it's not too bad. So this is the data that we just simulated. So you see there is somehow this slow varying frequency component with kind of a full circle, that's not a circle, at 0.5, I don't know, at 2, I can't really say it, but there's a slow varying thing, and there's quite a lot of this high frequency. Maybe let's make this a little bit higher, how it looks then. Oh, this is one cosine component here. Don't see, this is maybe not that easy to see because there's something on it. Scale that a little bit down. So I don't know. I mean, one can play with these things. Then it looks like this. And let's scale that back. And make this weaker. Don't know what this contributes anyway. This is how the signal looks. If you want to have it look a little bit more like completely real data, you can add a little bit of noise. But you just need to see that the scaling is roughly okay-ish. That is too low. Looks more like real data, although it is also looks like quite some artifactual data. Let's do a 10 Hertz. Let's do some alpha oscillations here that completely mask everything else. Yeah, whatever. So data. So the maybe let's add no noise. I mean, this also adds noise on each iteration. So we use noise-free data here for visualization. So that's the data. And now let's compute the discrete Fourier transform of it. We've of course already done that, but now we need to give it some interpretation. And this is the thing, the interpretation that we look at from an applied perspective today, essentially because I can't really explain where this is coming from. So the one thing is that the discrete frequencies, so we get discrete values out, right? So we get these y values out that we computed here. The question is which frequencies they refer to. And they refer to the frequencies j divided by n times the sampling frequency of the signal. So I'm telling you this, and today we don't discuss why this is the case, because this would need some more intricate interpretation. But the thing is, you put in data that has a specific sampling frequency, and what you get back from the discrete Fourier transform is the magnitude and phase information for a set of discrete frequencies, which is determined in terms of the frequency, the sampling frequency of the data and the number of data points. Yeah? That's how it is, applied setting right now. Then our discrete Fourier transform is just y, d. And then another thing about the discrete Fourier transform is the following. Let's scale, maybe not, is that, this we can see again here, that what happens here is in terms of the CK, there we had this complex conjugates. Yeah, remember that if you go back all the way, this goes into this, but what I'm after is this here. So our CK were defined in terms of AK and BK for the ones that are negative and for positive ones. Yeah, so the AK and the BK that go into this, they are the same, of course. So with the CK, you have the complex conjugates of the AK and BK. So you have them essentially twice. This is also where this 1/2 factor comes from. Now for the discrete Fourier transform, what happens is that these coefficients are mapped onto the first and the second half of the output. Again, this would require more theory to trace that in every detail, but what this means is that the first half of these coefficients here that we get and the second half are the same, but in complex conjugate form. So if we want information about frequency, magnitude, and phase, we can concentrate on the first or latter half. And again, this mapping between the CK coefficients that repeat themselves and switch actually at 0 versus the discrete coefficients that start at k being 0 and then go to n-1. This requires a little bit more theory, which we haven't discussed yet. But applied setting, we just throw away half of what we get out of the discrete Fourier transform, which is also what you do when you do a fast Fourier transform, of course. So you already get used to it, throwing away half of the things. To explain why this happens, maybe next time. This is the discrete frequency space. And this is our DFT. This is, consider do I have something here? No. Roughly. And then, of course, we discussed last time that we can give interpretations to these coefficients if we look at their real and imaginary parts. So we consider, I mean, what we could also do is to add the complex conjugate of the first half to the second half. Then we wouldn't have to do this 2 times real, I guess, if I'm not mistaken. But we might as well do it like this. So these are our CK essentially. Well, we might, these are essentially our CK. Then we look at the real part of these and at the complex part. And then, of course, we can look at the magnitude. Decay by using this thing that we did last week with the vector in this 2D plot. I hope you remember that. It was before the Jacobs seminar. So these were our frequency magnitudes. So now I've written quite some stuff here, and I guess there are some bugs somewhere. So let's have a look. Almost didn't go all the way. So we're here now. So let's first look what we have. These are our frequencies. They go from 0 to 1/2 the sampling frequencies, and these are our, no, these not. These are our associated powers. So let's plot the whole thing now. So now first with essentially no annotations and in not a very nice figure format. And let's have a look. Something, oops. Oh, it's a little bit long and a little bit too fine scale. So let's cut back on this and maybe only look at using some bad programming, first 20 frequencies. So now what do we see? It doesn't make any sense. We have what we specified for our data were the frequencies 0.5, 1, and 10. And here in the lower plot we have frequencies now. So this is 0, this is 5, and we have this is 1. And we have, well, we can actually cut that back even more, then it might be easier to see. So we have, that's 5, so 1 is 0.5, or almost 0.5 here. In any case, this is our 0.5 frequency, and this has was given an amplitude 1, so this is what we see here. 1 was given an amplitude 0.1, so that's here, and 10 was given amplitude 1. So we recover our input. So let's change this a little bit so that we see something else. So what I'm showing here is essentially that some parameter recovery. So here we specify parameters of some data, and now we estimate or evaluate these parameters, and we see that we recover the parameters that we put in, which is always good. So this works. Maybe let's put in some other frequency. Let's put in a 60 Hertz component and have a look at that, up to 100. So you see that there's this additional thing here, and you see that there's this additional 60 Hertz peak here. Yeah? I'm happy. I'm very happy because this worked. I don't know how happy you are, but so this shows that by implementing this discrete Fourier transform formula, you can look at the frequency magnitude in this setting by, first of all, knowing that the discrete Fourier frequency space is given by this formula. And this is what I said multiple times. I'm not justifying this today. This comes a little bit out of nowhere. And then by looking at the first half, this is justified in the sense that we have the CK, which repeat themselves in conjugate form after 0. And then by the formulas that we used, developed last time in terms of looking at the magnitude. Yeah. So that's discrete Fourier transform almost. So I hope I manage to maybe find an intuition why exactly these discrete frequencies come out. This is also fairly important because if you think that the discrete, it makes intuitive sense, but it's also important. So if you think you have some data and you have data of length n, then and a given frequency and a given sampling frequency, then what you can get out of the Fourier transform is not any frequencies, but you can get out the frequencies divided by n. Yeah, so it always depends exactly on your data set. So that's why this is important. The other thing is that when people compute Fourier transforms in real life, in NumPy or MATLAB, they don't use this because it's too slow, but use what is called the fast Fourier transform. And what the fast Fourier transform algorithm is, that's what I want to discuss next time. So, questions? Yes.
Okay, only to understand the signal better. The amplitude in terms of neural activity would be like the number of cells which fire in this specific frequency. Well, it's the strength of the signal, but normally the strength of the signal in cells would be the frequency, right? Because action potentials are included in. But so the amplitude must be.
So this relates. So if we talk about EG, so yeah. I'm basically now I mean, this of course obviously artificial data. So if we talk about EG, the fundamental model for what one gets at the electrode on the scalp in terms of biological origin, the idea is that what is measured there is the postsynaptic potentials of pyramidal cells. And what one then sees there, the idea is that this is the synchronized activity of input to pyramidal cells over a large area of cortex. In general, that's the idea, but then if you really want to know more about this, so one thing is you can watch this in the EEG course where I explain a little bit more. The other thing is if you really, really want to know the relationship between single neurons and EEG activity on the scalp, then you go into computational neuroscience and modeling thereof. So there essentially not much is known. If we model EEG data using neural mass models like we did in, for example, the Steele differential equation framework, which is the DCM framework, essentially, then what one models actually is a population of neurons, and then the states of this model are the voltage of a population of neurons. So let's say 1 million neurons, they have a joint voltage, and these are then translated to the scalp using essentially the Poisson equation implemented in a linear forward model. So if you which is why when you have something like this in the EEG, the 60 Hertz is likely in line noise, or 50 Hertz, that's just from the power socket. Synchronized activity in terms of EEG, refers to some synchronized input at the cortex, but this is as specifically as one gets actually with that. Although it's of course very interesting, and biophysical modeling of EEG data is an awesome field and should be done much more, but people like more to see blobs on the brain and discuss how much power they should have. So, any more questions? Because I think I'm running over. Yeah, I'm running over, but that's okay. Yep.
So basically what we did was we set parameters for omega, AK, and before you said EK, you set it to 0.
Yeah.
And like the plot that is below just kind of shows us what we did.
No, this shows the magnitude information that we, it shows us what we did, what we said, but it also shows the interpretation of the discrete Fourier transform outcome, right? So normally you don't know what you put in. Normally you have some data that looks like that and you get out something like this. And I just simulated data where we know what's going on, so to actually check that our discrete Fourier transform also makes some sense. Normally, Arthur Jacobs would give you this data and say, analyze it, and then you would show him this, and then you would say, oh, better power,
okay,
working memory.
And the graph below actually is like where we want to get, so that is our frequency domain. And
yeah, it's not annotated because I didn't make the effort, but yeah, that's exactly what it is. Yeah, so that was now real data analysis, and next time more real data analysis in terms of fast Fourier transform, and I hope to look into why this is the frequency space. Yeah, okay, then let's have a break until 10:15 and then go to the other course.